In this video, I'm going to be showing you how to solve the Schrodinger equation, the time-dependent Schrodinger equation, using the method of separation of variables. And specifically, I'm going to be showing you how to solve this partial differential equation for when v of x is not equal to 0. In the previous video, I showed how you can solve Schrodinger's equation for when v of x is equal to 0, and in that case, it was actually quite a simple process because letting v of x equal to 0 removes that entire term. And so with that simplification, it becomes a lot nicer and cleaner to solve. But in this case, we're not going to let v of x equal to 0. We're going to say it's some function, some arbitrary function v of x, and we want to solve for psi of x of t. So again, the goal is to solve for psi of x of t. We can use separation of variables, the technique of separation of variables. And if you're unfamiliar with separation of variables, I have a video on that. Please go look at that. We're going to use this method of separation of variables. So we're going to assume that psi of x of t is a product of a function of x and a function of t. And I'm actually going to let this equal psi of x times t of t. So psi of x of t is a product of psi of x and t of t. And so the first step in solving this partial differential equation, so let's say solve. The first step in solving this partial differential equation is to substitute psi of x t of t for psi of x of t in the above equation. So that's going to result in this. So IH bar partial t psi of x t of t, which is equal to minus h bar squared over 2m partial x squared of psi of x t of t plus v of x times psi of x times t of t. So now that we've done that, notice the partial derivatives on the left and right hand side of the equation. This is a partial derivative with t. This is a partial derivative with x, which means for the left hand side of this equation, this partial derivative with respect to x is not going to affect that. It's not going to affect psi of x, right? Which means we can factor that out such that we get IH bar psi of x times partial t of t, and that's equal to minus h bar squared over 2m, and the same thing on this right hand side. This is a second partial derivative with respect to x, which means that this function t of t is not being differentiated, right? Because that's a function with respect to time. So we can pull that out. So we get partial x squared times psi of x plus v of x psi of x t of t. Taking those derivatives respectively, we get IH bar psi of x t prime of t is equal to minus h bar squared over 2m t of t psi double prime of x plus v of x psi of x times t of t. So now that we have it in this form, what you want to do is you want to divide by psi of x t of t. And the reason you want to divide is because what that's going to do is literally get your equation in a form such that the x variable is completely separated from the t variable. In other words, on one side of the equation, you will have an expression with only t, and on another side of the equation, you will have an expression with only x. So if we do this division, IH bar psi of x t prime of t divided by psi of x t of t, and that's equal to minus h bar squared over 2m t of t psi double prime of x divided by psi of x t of t plus v of x psi of x t of t divided by psi of x t of t. Notice that various things cancel. For example, these cancel. In the first term on the right-hand side of the equation, the t of t's cancel. On the left-hand side of the equation, the psi of x's cancel. And so if you notice how this simplifies is that you get IH bar t prime of t over t of t is equal to minus h bar squared over 2m x psi of x double prime over psi of x plus v of x. All of the time dependence, t, is on the left-hand side. All of the spatial x dependence is on the right-hand side. Now, because of this, if we vary x, t has to vary in such a way that these two expressions are equal, and we know that they have to equal the same constant. And again, we're talking about Schrodinger's equation, which, when we talk about wave functions, we often talk about particles. And so we're going to take the same constant, take the constant that these two are equal to as the total energy E. And so what we have, what we have is IH bar t prime of t over t of t is equal to E and minus h bar squared over 2m psi double prime of x over psi of x plus v of x is equal to the total energy E. And we have to solve each of these separately, and then once we do that, we'll be able to put it all back together to find a general form for psi of x of t. So solve IH bar t prime of t over t of t is equal to the total energy E. So we're going to start with this. We're going to start with the left-hand side here. We're going to solve this differential equation. So IH bar t prime of t over t of t is equal to E. If we rearrange this to get an expression explicit for t prime of t, we get t prime of t is equal to E over IH bar times t of t. So all I did is multiply by t of t and divide by h bar so that I can essentially isolate t prime of t. And if you notice, t prime of t is directly proportional to t of t by some constant, right? Where this constant is E over IH bar. So from calculus, you know that anything of this form, where you have the first derivative of a function directly proportional to itself, it has the form of an exponential, right? So we know that t prime of t is going to be some exponential. AE to the E t over IH bar. And so this is really the general solution for, this should be not a prime, t of t. So this is our general solution for t of t. Now what I'm going to do is, in this exponent, I'm going to multiply by I over I. So if you multiply by I over I in the exponent, you get t of t is equal to a e to the minus I et over h bar. And then there's nothing special there. I just kind of rewrote that just to make it look nicer. And that is really the form you want it in. So that is the general solution for t of t. Now, the part that is interesting is when you solve for the spatial part with respect to x, right? So minus h bar squared over 2m times psi double prime of x over psi of x plus v of x is equal to e. This is where it gets interesting because we have this this v of x function here. When v of x was 0, this term went away. And it was a lot simpler to solve. But now we have some potential function v of x. And the first thing you want to do in solving this is to multiply by psi of x. So if we multiply by psi of x in this equation, you get minus h bar squared over 2m psi double prime of x plus v of x times psi of x is equal to e times psi of x. Now, I kind of want to show something here. So if we factor out psi of x on the left-hand side, and right now I'm just going to rewrite it just so you can see a little clearer, and then I'll factor it. So we have this now, but if we factor out psi of x, you get minus h bar squared over 2m d squared dx squared plus v of x times psi of x is equal to e times psi of x. Now, pause the video if you'd like and think about what does this look like? What does this look like? You have this here multiplied by psi of x, and that's equal to some constant times psi of x. What this is an eigenvalue equation, right? Psi of x is an eigenfunction, and e is an eigenvalue. So I think it's really important to notice that. It's kind of interesting how we have this eigenvalue equation, but let's get back to solving this equation here. So minus h bar squared over 2m, I'm going to just kind of like redistribute psi of x here. So minus h bar squared over 2m psi double prime of x plus v of x psi of x is equal to e times psi of x. Now what you want to do is you want to move this term over to the left-hand side and this term over to the right-hand side. And you'll see why in a moment. So if you do that, you get minus h bar squared over 2m psi double prime of x minus e times psi of x is equal to minus v of x times psi of x. And this is where it gets interesting. You might look at this and say, well, I mean, I don't really know how to solve this, or what do we do moving forward? What you want to do is you want to let psi of x equal the Fourier integral of its Fourier transform. So remember that the Fourier transform of a function f of x is equal to the integral from minus infinity to infinity of, well, g of alpha times e to the I alpha x dx, where g of alpha is the Fourier transform of f of x. So if you take the Fourier transform of f of x, you get a function g of alpha, which is again equal to the Fourier integral 1 over 2 pi times the integral from minus infinity to infinity of f of x times e to the minus I alpha x dx. This one is with respect to alpha. This one is with respect to x. So what we're going to do is substitute psi of x for its respective integral. So psi of x, so just like f of x is equal to the integral of its Fourier transform, we're going to, psi of x is also equal to the integral of its Fourier transform. So psi of x is equal to the integral from minus infinity to infinity of psi tilde of k e to the I kx dk. And I'm going to use the variable k here instead of alpha. But if you're a little confused, psi tilde of k is the Fourier transform of psi of x. So psi tilde of k would be something like 1 over 2 pi times the integral from minus infinity to infinity of psi of x e to the minus I kx dx. Right? So we can say this. We can replace psi of x for this integral, that integral. And that's exactly what we're going to do here. We're going to substitute psi of x for the integral of its Fourier transform, for that integral. So just to make some space, we're going to move down here. So minus h bar squared over 2m times d squared dx squared. So this is psi double prime. This is psi double prime up here. But that's the same thing as d squared dx squared of psi of x, right? Well, let me do this. Psi of x minus e times psi of x, which is equal to minus v of x times psi of x, right? Okay, so now I've kind of written this entire equation explicitly so that you can see psi of x. So minus h bar squared, we're going to make the substitution now. We're going to make the substitution d squared dx squared of, so we're substituting psi of x. We're substituting psi of x for the integral from minus, and I'm going to write it in blue just so you can see it. The integral from minus infinity to infinity of psi tilde of k e to the I kx dk. So I'm going to write these in blue just so you can see where I'm getting things from and what those integrals are. So the integral from minus infinity to infinity of psi tilde of k e to the I kx dk. Sorry, dk. And that's equal to minus v of x times psi of x. And you might be wondering why I didn't replace psi of x for its corresponding integral on the right-hand side of this equation. And I will explain that now, actually. What we're going to do is we're going to replace v of x times psi of x on the right-hand side of this equation. But we're not going to replace just psi of x with its corresponding integral. We're going to let v of x times psi of x. And again, we can do this. We're going to let v of x times psi of x be some function f of x. Big F of x. Big F of x. Okay? So doing that, and that's totally legal to do, we're just simply saying that v of x times psi of x is some function. It's some function. It's a function, big F of x. Big F of x. It's a function of x. So let's substitute that. So we get minus h bar squared over 2m d squared dx squared. And I'm going to write all this out so you can see it. The integral from minus infinity to infinity of psi tilde of k e to the I kx dk minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk. And that's equal to minus f of x. Right, so we've written this down. We've replaced psi of x for its corresponding integral. And we want to simplify it further. That's the goal, is to simplify this further. So the first thing, if you notice, is that this derivative here, this second derivative here, we can move that inside of this integral. Minus h bar squared over 2m, the integral from minus infinity to infinity the integral from minus infinity to infinity of d squared dx squared psi tilde of k, and let's be more explicit what we're taking the derivative of here, e to the I kx dk, and that's minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk is equal to minus f of x. Okay, so if we take this derivative in here, notice that psi tilde of k is not dependent on x at all. It's not dependent on x. And so really, we're just taking the derivative of this exponential part here, because psi tilde of k is not dependent on x. So it's minus h bar squared over 2m, the integral from minus infinity to infinity, psi tilde of k, d squared dx squared of e to the I kx. So the second derivative of e to the I kx with respect to x is ik times ik. E to the I kx dk minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk is equal to minus f of x. Okay, so one more simplification step. I'm just going to multiply these two together just to get a simplified expression here for the most part. I guess that's subjective, right? What does simplified look like? This is, wow, lots of integrals. But minus h bar squared over 2m, the integral from minus infinity to infinity of psi tilde of k times, this is going to be, I times I is negative, so this h bar squared over 2m is going to become a positive, k squared e to the I kx dk minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk, which is equal to minus f of x. Now, at this point, what we're going to do is we also want to let f of x equal its Fourier transform. And you could have easily done this earlier. We could have easily done this earlier where we set v of x times psi of x as a function f of x. And then we could have replaced f of x for its Fourier integral. But we didn't, and we can do that now. So f of x, we're going to replace f of x by its Fourier transform as well. Or its corresponding integral, sorry. F of x is equal to the integral from minus infinity to infinity of f tilde of k e to the I kx dk. So this integral is equivalent to f of x. So whatever the Fourier transform of f of x is, which is going to result in f of k, this integral here is equivalent to f of x. So we can substitute it for f of x, right? And so if we do that, let's substitute f of x for its corresponding integral in the above equation. So we get h bar squared over 2m, the integral from minus infinity to infinity of psi tilde of k times k squared e to the I kx dk minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk. And that's equal to minus the integral from negative infinity to infinity of f tilde of k e to the I kx dk. And you might be looking at it at this point and saying, well, where do we go from here? And how are we going to solve for psi of x, which is what we wanted to do in the first place? Well, if you notice, what we can do is move this integral, this entire thing, over to the left-hand side. And so we get the sum of these various integrals equal to 0. And what we'll see is this actually really interesting, something really interesting happens. So let's move this integral to the left-hand side of this equation. So we get h bar squared, and I'm going to take this k squared here and move it in front of the integral just because it looks nicer. H bar squared k squared over 2m, the integral from minus infinity to infinity of psi tilde of k e to the I kx dk minus e times the integral from minus infinity to infinity of psi tilde of k e to the I kx dk plus the integral from minus infinity to infinity of f tilde of k e to the I kx dk is equal to 0. So let me rewrite that. E to the I kx dk is equal to 0. So all we did is moved over the integral for f of x, which is this one here, to the left-hand side. Now notice that all of the integrals have the same bounds. We're integrating with respect to the same variable k. And so really what we can do is move that integral out, essentially, right? Because of the sum rule, we know the sum rule for integrals, so we can move that integral out. Remember that this integral from a to b of f dx plus the integral from a to b of g dx is equal to the integral from a to b of f plus g dx. Right, so using that, we can rewrite this. So if we rewrite it, we get the integral. Let's make that a little bigger. The integral from minus infinity to infinity of h bar squared k squared over 2m psi tilde of k e to the I kx minus e psi tilde of k e to the I kx plus f tilde of k e to the I kx dk. And that's equal to 0. Notice that every single term within this integral has a factor of e to the I kx, which also means that we can factor out the e to the I kx, which is exactly what we're going to do. The integral from minus infinity to infinity of h bar squared k squared over 2m psi tilde of k minus e psi tilde of k plus f tilde of k e to the I kx dk. And that's equal to 0. So something really interesting happens here. Because this integral is set equal to 0, first of all, remember that, recall that the set of all functions e to the I kx are linearly independent. They're linearly independent. And because they're linearly independent, when you sum over all of them, like we have here, we're summing, so this, right, we have this term, and then we're taking this sum, this integral from minus infinity to infinity over all k, and because of the fact that these exponentials here, e to the I kx, because they're linearly independent, in order for this integral to equal 0, this term here multiplying the e to the I kx has to equal 0. It has to. It needs to equal 0, right? That must equal 0 in order for this integral to equal 0. So what we can do is at this point, and this is a major simplification, which is really nice, right? This simplifies our problem quite a bit. Because of the fact that those exponentials are linearly independent, this integral, we can say that h bar squared k squared 2m psi tilde of k minus e psi tilde of k plus f tilde of k has to equal 0. Has to equal 0. So at this point, what we can do is begin to really solve for psi of x. Really, and this is where it becomes really clear. Notice that we can move the f tilde of k over to the right-hand side. So if we move f tilde of k over to the right-hand side, you get the following minus f tilde of k. If you factor out psi tilde of k on the left-hand side, you get psi tilde of k times h bar squared k squared over 2m minus e, and that's equal to minus f tilde of k. Solving for psi tilde of k, if we solve for psi tilde of k, that's equal to minus f tilde of k divided by h bar k squared over 2m minus e. Now at this point, something interesting is that we've solved for psi tilde of k, but what we want to solve for is psi of x. Remember? So psi of x, if we want to solve for psi of x, can we not take the Fourier transform of both sides? Or the inverse Fourier transform of both sides? And the answer is yes, you can. So you can move between psi of x and psi tilde of k by taking those integrals, those respective Fourier integrals. So psi tilde, so let's just remind ourselves of what those integrals are. So psi tilde of k is equal to 1 over 2 pi times the integral from minus infinity to infinity of psi of x e to the minus I kx dx. And psi of x is equal to the integral from minus infinity to infinity of psi tilde of k e to the I kx dk. Right? So we can substitute for psi tilde of k. So psi tilde, we have an expression for psi tilde of k. And that's equal to this right here. Well, in order to go back to psi of x is equal to this integral here, right? So we have an expression for psi tilde. This is our expression for what psi tilde of k is. So if we're seeking to find psi of x, that's going to be equal to the integral from minus infinity to infinity of psi tilde of k times e to the I kx dk, right? From what we've done so far, we've been able to solve and find an expression for psi tilde of k. So if we take the inverse transform of both sides here and here, right? So in this whole expression, this whole equation here, if we take the inverse transform of both sides, we get psi of x on the left-hand side, right? We get psi of x, and that's equal to the integral from minus infinity to infinity of psi tilde of k. Well, psi tilde of k is equal to this whole thing here, So the integral from minus infinity to infinity, and I'm going to make this bigger, the integral from minus infinity to infinity of minus f tilde of k over h bar squared k squared over 2m minus e times e to the I kx dk. Okay. Now, remember we defined our function f of x earlier, right? We defined our function f of x, which was equal to v of x times psi of x. And remember that f tilde of k is equal to 1 over 2 pi times the integral from minus infinity to infinity of f of x e to the minus I kx dx. Right? So that is the equivalent integral for f tilde of x. So the Fourier transform of f of x is f tilde of x, and f tilde of x is equal to this whole integral here. Well, what we're going to do is we can substitute f tilde of k in this expression for this integral. And that's exactly what we want to do. So we have an expression for psi of x now. Psi of x is equal to the integral from minus infinity to infinity of minus, and this is going to get just a little bit messy, so minus 1 over 2 pi times the integral from minus infinity to infinity of big F of x times e to the minus I kx dx. And that is divided by h bar squared k squared over 2m minus e, and then times e to the I k x dk. So at this point, this is what we have as an expression for psi of x. And before we move on, I want to make a notation clarification. Notice that this x here is essentially different than these x's here. And so for notational purposes, just in terms of our integrals, we want to denote this as x prime and leave this as x, right? Because we're saying that these x's here in this integral and the integral with respect to x here is for this integral in the numerator, whereas this is different. And so with that, we can simplify this a little bit further. And it may not be totally intuitive as to why or how we're simplifying in this way, but what pops out is something interesting called a Green's function. So if we simplify, psi of x is equal to the integral from minus infinity to infinity of minus 1 over 2 pi times the integral from minus infinity to infinity of f of x prime e to the minus I kx prime dx prime e to the I kx over h bar squared k squared over 2m minus e dk. Notice that what we can do is move this exponential inside here. And the reason we can do that is because we're differentiating with respect to dx prime here. In this inside integral. And we're not changing the fundamental integration location for this exponential term, right? We're not changing it in an illegal way mathematically. So it's just simply a mathematical manipulation that we can do. And so psi of x is equal to the integral from minus, and I'm going to make this integral really big, the integral from minus infinity to infinity of minus 1 over, well, let's do it like this, minus 1 over 2 pi times the integral from minus infinity to infinity of f of x prime e to the minus I kx prime e to the I kx dx prime dk. And I'm going to move this constant term down here inside this integral. H bar squared k squared over 2m minus e. There we go. Now, I'm going to write this integral just a bit bigger. Minus infinity to infinity. And we're going to do just a couple more manipulations on this until what we see is what's called a Green's function. So psi of x is equal to the integral from minus infinity to infinity of minus 1 over 2 pi times the integral from minus infinity to infinity. Now, with these exponential terms up here, we're multiplying them, right? Same base, we can add the exponents. Pretty simple. This is going to be e to the I k x minus I kx prime f of x prime dx prime dk over h bar squared k squared over 2m minus e. Now, we can reverse the order of these two integrals. So we can integrate first with respect to dk and then dx prime second, right? That is mathematically legal and it's mathematically correct. So we can completely do that. So psi of x is equal to minus the integral from negative infinity to infinity of 1 over 2 pi times the integral from minus infinity to infinity of e to the I k x minus x prime, and as all I did is rewrote the exponent here, this. I rewrote that as this. So e to the I k x minus x prime over h bar squared k squared over 2m minus e dk f of x prime dx prime. What we can do, let's move this negative down into the denominator here. Just for compactness. This is positive, and then what happens here is that the order of these two switch. So it's e minus h bar squared k squared over 2m. And really, at this point, we've come to a pretty good solution. And you might be thinking, that does not look like a good solution. Well, I'm going to write this a little bit more clearly, really explicitly, just so you can see. 1 over 2 pi, the integral from minus, wow, that is a bad integral. The integral from minus infinity to infinity of e to the I k x minus x prime, e to the I k x minus x prime, divided by e minus h bar squared k squared over 2m dk f of x prime dx prime. Okay, this is what's called a Green's function, and we denote it g of x minus x prime. It's called a Green's function. And so, what we're left with, this integral here, 1 over 2 pi times the integral from minus infinity to infinity of all of that, this here, this is called a Green's function. And so what we're left with is psi of x is equal to the integral from minus infinity to infinity of g of x minus x prime times f of x prime dx prime. And so I have a video on Green's functions if you'd like to go check that out. I delve a lot more into what Green's functions are, where they come from, how they fit in to all of this. I'm not going to go into a lot of detail about Green's functions in this specific video, but this is essentially what we have for psi of x. And we already found t of t. Remember, that was the time part. And we just found psi of x. And so with that, we have constructed the two parts for what we have been looking for, which is psi of x of t, right? So taking what we found from the previous parts, we found that t of t is equal to a e to the minus I et over h bar. And we just found this expression for psi of x. And so psi of x of t, remember we defined that psi of x of t is a product of psi of x and t of t. That's what we defined initially. And so psi of x is equal to a e to the minus I et over h bar times the integral from minus infinity to infinity of g of x minus x prime f of x prime dx prime. And so that, at this point, is our final solution, and is what we've been looking for. So, just to recap, we solved the time-dependent Schrodinger equation for the situation where the potential function v of x is not equal to 0. We found the time part, we used separation of variables, we found the time part, t of t, and we found the position part, psi of x. Have a good one.